Hello, welcome back viewers to the MTN Teleschool second session. We thank you for being with us again. My name is again James Kabuye, and I'm specialized in physics. We are going to go through now since 21 up to 40. But before we do that, let me take you back to question 7, which we dealt with in our first session. Question 7 was talking about vector diagrams representing 4 forces acting at the same time and at the same point x. Understand, viewers, that 2 important scenarios occur there. 1, if 2 of the forces are such that they are, as I'm going to draw here, at point x, and then we have this force which is 3 newtons, we also have 4 newtons, and at the same time we have another 2 forces acting in this pattern, 3 newtons and 4 newtons in this manner, and this is also x. We must be very sure that these x's are referring to the same point. If these 2 x's are going to refer to the same point and culminate into the point bigger x, this bigger x which they have mentioned here to be the resultant at this point x, what is the resultant force at point x? Then we can say that we draw this point x, which is big, and we put all these forces that are available, like this one, we put 4 newtons. We get this one, we put it here, we will have 4 newtons. We get this one, we put it here, we put 3 newtons. We get this one, we put it here, and we get 3 newtons. In this scenario, viewers, then we are likely to get the resultant force as 0 newtons on the bigger point x. But without this scenario and treating these x's as different x's and 2 forces acting on each totaling to 4, then the resultant force still remains 5. 4 squared plus 3 squared, the square root will give us the resultant, which is 5 newtons. That is one clarification which I wanted to make very, very quickly before we move on to the other questions that we are going to see in this session. I invite you to go to question 21 now. Question 21. Question 21 reads, what do the pitch and loudness in a sound wave depend on? Pitch is the one that determines the frequency of the sound, and loudness is actually determined by the amplitude of oscillation. Amplitude means that how much energy have you given to this wave, and frequency means how fast is this vibration occurring, and what is its intensity. That is what determines the pitch. So the pitch is determined by frequency. In fact, we can say that the frequency depends on the pitch, and amplitude also dictates the loudness. Question 22. Question 22. Question 22. in order to solve this problem properly, question 22, the question reads, the diagram below shows a ray of light traveling from substance X to air. Okay, so let me just draw this quickly so that we see what is happening. So this is our normal, and this is the ray that is coming to hit the boundary here, and it's getting refracted into the air, and this is substance X. Now, when we look at this, what we must understand is that when people are working out refractive index, basically, of a substance or refractive index of a material, they are talking about a ray of light traveling from, if you like, from a vacuum into that particular medium. So when light travels from a vacuum into a medium, and we get the angles of incidence and refraction, and we divide them, we get the refractive index of that particular material, which is denser. So in this particular case, as you can see, the ray now is coming from a dense medium to a less dense medium. And now they are asking us to find the refractive index of substance X. We must go into a theory and notice what is happening here. It's the principle of reversibility of light which is needed here, to say that if light takes a certain path to go in a certain direction, for example, in this case, let's see, it starts from A going to B, then this principle of reversibility of light states that if light were to come back to the original position, then it would use the same path. That is a principle of reversibility of light. So in order for us to get the refractive index, we must rely on this principle, so that we assume now that light is going to come from the air into the glass block. In which case now also we must understand something again, that when we are measuring the angles of incidences and angle of refraction, it must be such that we are measuring from the normal. And we must make sure we are measuring from the normal, and this is our normal. So when we look at this very, very seriously, we see that we are going to see now a ray of light changing direction. I'm going to rub this, the initial arrows, I'm going to rub this, and then draw another ray now, which is similar to the old one, but the arrows will be reversed, because we are using the principle of reversibility of light. In this case now, we are seeing a ray of light that is going to come from air into the substance X, so that we can easily get the refractive index of substance X. In this particular case now, we see that the angle of refraction becomes 90 minus 50, which means 40 degrees. Okay? And then now we have this angle which becomes 60 degrees as now our angle of incidence. Why? Because these angles of incidences and refractions should be with respect to the normal. So we are checking from the normal up to here 60 degrees, and now from the normal up to here it's 40 degrees. Now we have our I, which is 60 degrees. We also have our R, which is 40 degrees. Then we can say that the refractive index shown by a Greek letter shown here is equal to sine I over sine R, so that we get sine 60 degrees divided by sine 40 degrees. When we do this, we find 1.53 as the refractive index. We move on to question 23. Question 23 reads, The diagram below shows a mirror and two images, A1 and B1, whose objects are A and B respectively. Understand that A and B have not been shown in the diagram, but they want us to determine, they are saying if object A is removed and the mirror moved to where object A was, determine how far the image of B will be from its object. Rather confusing question, but let's see what is happening. Let's go back and see what is happening now. We first have this diagram, which is going to show the initial scenario where we have we now have a mirror placed here. And then what we have is that we have object here, which is B1. We also have object here, image here, which is A1. So A1 and B1 are images of some objects. Okay, fine. So the distance of image A1 from the mirror is 1.7 meters. The distance of B1, the image B1 from the mirror is 3.7 meters. From this first diagram, we can tell that the first object A is here, the other object B is here, and the distances must be the same. So the distance from here to here should be 1.7 meters, and this distance also should be 3.7 meters. So we have this scenario now. What they are saying is, if object A is removed and the mirror moved to where object A is, so that means that we draw another scenario here where A was, we put the mirror, and then I think that then where B was remains there. Okay, so that means that since now the mirror has been brought where A is, and the distance from B to the mirror, the distance of B from the mirror now, we see that it will be now 2 meters from the mirror. We expect that the image of B should be the same distance from the mirror, B1, which is another 2 meters. So this is the normal situation we expect, so that we say if this new image, determine how far the image of B, which is this one, will be from its object, the object which is here. So we can say that it is 4 centimeters. That's what we can say. 4 centimeters. But then, if they are asking us about the how far this image of B will be from its object, we must be told whether it's the original position of B1 or not. But for now, the answer should be 4 centimeters. That is the right thing. Because the distance of the image from the mirror should be the same as the distance of the object from the mirror. We move on. Question 24. A man sees a stone at the bottom of a pool of water. Can we see this question? Right. So when we check on this question, what we see is that we have rays of light that are emerging from a stone and going into the eyes of a viewer. And we must understand that there are principles that govern these rays when they move from one medium to the other. When a ray of light, let's start with A, ray A. It starts from the object and reaches the boundary. We must draw the normal at that boundary. And we notice that that ray is hitting the surface at right angles. And such rays which hit surfaces at right angles pass straight without getting refracted. So A is wrong. When we go to B, yes, it agrees, because when we draw the normal at this position, let me just draw something roughly for B. This is the stone, and the ray comes and hits the boundary and gets diverted. Then we can draw the normal here, and we see that this medium is less dense than this medium, so the ray bends away from the normal. So it agrees, this B. C, it shows as if the ray will pass straight, and yet is hitting the surface at an angle, so it's wrong. And D also shows as if the ray of light is going to bend towards the normal, and then so it shows that that is not correct, because water is denser than air. We move on to question 25. So the correct answer is B. Two identical pieces of soft iron were placed inside the solenoid as shown in the diagram below. Which of the following would happen when switch S is closed? We must understand that when we talk about solenoids and current flowing through them, we must know the direction of the current first in the solenoid by first noting that conventional current moves from positive to negative. And therefore, when we do that, we put an arrow. Let me just draw this very quickly. If we have current which is coming, and it's like this, and like that, and like that, and like that, it shows that current is moving in that. If current is moving in this direction, then we must check out in these directions, these two. We check here the direction of the current. If the current is going clockwise at this point, when we view from this side, if the current is going clockwise, then that magnetic substance placed inside there is going to generate, is going to have a south pole at that end, because the current is going in a clockwise manner. So then the other end becomes north. When we check on the other side also, we see that we are going to have the south pole there and the north pole at the end. Okay, when we do that and we notice that this is the scenario, then we check the behavior of the two magnets that would have been produced as a result of this. So we see that A will move to the right and B will move to the left. 26. Which of the following materials is correctly described? So here they are just talking about magnetic properties of steel and iron. Magnetic properties of steel and iron. We know that iron is easily magnetized and steel is not easily magnetized. And once magnetism has taken place, steel keeps magnetism for a long time, while iron does not retain magnetic properties for a long time. So therefore iron is used to make soft magnetic materials, while steel forms permanent magnets. So the first row will tell us the correct answer, which is A. Material ion property is demagnetized and used in the electromagnet. We can move on to 27. A negatively charged rod is held close to a metal sphere which is earthed. Which of the following describes the change on the metal sphere? So, since we are bringing a negatively charged rod very close to a neutral sphere, the neutral sphere has the charges inside equally distributed initially, equal positives and negatives, equal positives and negatives, and equally distributed, but the presence of the negative charge causes these electrons to be repelled to the earth. When these electrons are repelled to the earth, then this sphere remains positively charged. The sphere remains positively charged. Remember that in this particular scenario, protons are positively charged particles are not moving. What is moving is electrons, and so they are causing an excess of positive charges on this sphere as the other electrons are repelled. The electrons are repelled to the earth. So the correct answer is the sphere becomes positive because the electrons are repelled by the rod. Question 28. If a conductor in the 6 ohm resistor. How do we solve this problem? We must know the total voltage, which is in this case 6 volts. Then we say also that we must find the total resistance in the entire circuit so that we can find out how much current is flowing in this particular circuit. Let's try and do this. What is the total resistance here? These two resistors are in parallel. Therefore, if we find the effective resistance of these two, it's as good as removing them and replacing them by only one of the value that we are going to find. So, 1 over total resistance is equal to 1 over 6 plus 1 over 12. coming from 1 over R total to be equal to 1 over R1 plus 1 over R2. Arising from there, we get 12 as the common denominator, and we get 2 plus 1 equal to 1 over R. So 1 over R becomes equal to 3 over 12. So that R becomes 12 over 3, which is 4 ohms. If we removed these two resistors, we would replace them by one 4 ohm resistor, which will be in series with this 2 ohm resistor. So then we can say that the total resistance becomes 6 ohms coming from 4 plus 2. Okay, coming from 4 plus 2, which should be equal to 6 ohms. We now have the total voltage and the total resistance. We can now say that V is equal to IR, so that the total current in the circuit is V over R. V is 6 and R is 6, so that we get 1.0 amps. This is the current flowing in the whole circuit. But the question says, what is the current in the 6 ohm resistor? So we can first, in fact, find out what is the voltage across the 2 ohm resistor, and that will tell us the voltage across the 6 ohm and the 12 ohm in parallel. The 6 ohm, let me go back to this diagram. The voltage across these two is the same. It's only different from the voltage across these 2 ohms. So in the 2 ohms, we have V equal to IR, so that the current flowing is 1.0 times the resistance, which is 2, and then that will give us 2 volts. That means that the voltage across the 2 resistors in parallel is actually 6 minus 2, which is 4 volts. These two are at the same potential difference, which is 4 volts. Therefore, current, okay, we can say that IR is equal to V in this particular situation, where we say that in these 6 ohms, V is equal to IR. This is what we are now getting to here. So now we can say that the current is actually, we can say V over R should be equal to current, so that current becomes 4 divided by 6. This will give us 1/3, okay, which is 0.33 amps. That is the current flowing through 6 ohm. A is the correct answer. We move on to question 30. Which value of current and resistance will produce a rate of energy transfer of 16 joules per second? This rate of energy transfer is actually power. So power is equal to VI. Power is equal to VI. But when we look at the values that we are given here, we are not given the voltage. So we can get V equal to IR and replace this in our equation, so that we get IR times I, so that we get I squared R. This is the equation that we are going to be using in order to determine which pair is going to be correctly represented and which one must give us 16 joules per second. Let's start with 1. When we say current is 1, and 1 squared times 4 just gives us 4, so it's wrong. 2 squared is 4, times 8 gives us 32. 2 squared is 4 times 4 gives us 16. So that pair is the correct pair which gives us the power of 16. So the answer is C for that question. We move on to question 31. The diagram below shows a resistor which color with color labels on it. Okay? Use the color code for resistance given below. Okay, we are given these color codes, as you can see. Now, let me draw something very quickly here, just for viewers to understand. If this is the resistor and this is the first color band, the second color band, and then the other one, and we have the fourth one, these are color bands. So we have the first, we have the second, we have the third, we have the fourth. What we can say is that we are told that this one is brown, this one is green, this one is red, this one is gold. The gold one at the end gives us the tolerance within which the resistor can operate. The first color tells us the first digit in the value of the resistance. The second color tells us the second digit, while the third one tells us the number of zeros that are present in this value. So, when we check on the key, we find that brown is under 1. So it means the first color tells us that we must have the 1, we must have 1 as the first digit. The second color, which is green, tells us that the second digit should be 5. Then the third color tells us the number of zeros we must add. In this case, we check and we find that it's red. Red gives us 2 zeros, we add them here. When we do that, we find 1,500, which is 1.5 kilo ohms. And then the last color gives us the tolerance within which it can operate. What is percentage tolerance? In this case, 5% plus 5% tolerance. So the correct value of the reading is 1.5 kilo ohms. We move on to the next question. The cost of electricity is 55 ngwe per unit of electricity. What would be the cost of operating a lamp rated 240 volts, 250 watts for 9 hours? We go back to these calculations and take note of the fact that 1 unit of electricity is the same as 1 kilowatt hour. So, we must make sure that 250 watts is taken to kilowatts, okay, which will be now taken to kilowatts will be 250 divided by 1000, so that we get 0.250 kilowatts. We already have the hours there, so we don't need to tamper with the hours. So we just say, okay, how many units were used then? It is 0.250 times 9 hours. Okay, so that we get, when we do that, and then we come and multiply to the unit cost, which is 55 ngwe, we are likely to get 1 kwacha 24 ngwe as the right answer. Okay, question 33. When we do look at this question, we notice very quickly that the diagram below shows a generator, whose coil is rotating in the direction shown. All the time a coil rotates in a magnetic field is going to generate an EMF, or if you like, a current in that coil. And this is conducted via the carbon brushes to the external circuit. And every rotation gives us some amount of voltage. And it must follow a sine wave all the time. It must follow a sine wave, because when the rotation, when this coil is actually rotating, there are points when it cuts the flux at maximum, and there are times when it is actually lying parallel to the flux. So when it lies parallel to the flux, there will be almost zero EMF generated. And it produces maximum when actually it cuts the flux at maximum. In this case, at 90 degrees, every 90 degrees, it's going to generate a maximum voltage, if you like, or maximum EMF. So A is wrong, B is not a sine wave, C is the correct sine wave, and D falls off. Question 34. The diagram below is of a transformer whose input is connected to a 240 volts mains. It is being used to light a 12 volt lamp as shown in the diagram. So I want to do very quickly this transformer, and we have this as our core, and then we have the turns here, we have the number of turns there. And here what we see is an alternating voltage of 240 volts, and the number of turns are 1000 turns. Here we have a circuit that is operating a bulb which is rated 12 volts and 3 amps. Okay, so this situation means that this is obviously a step down transformer, because we have less turns in the secondary coil and we have more turns in the primary coil. Now, assuming that the transformer is ideal, and then what is the number of turns in the output coil and the value of the input current? So we start with the number of turns. Two formulae, very important. Voltage in the primary divided by the number of turns in the primary must always be equal to the voltage in the secondary when divided by the number of turns in the primary. That is number one. This will tell us the number of turns. Okay, when we do that, what we see basically is that we have voltages, we have the number of turns one side, so we can substitute. Voltage in the primary is 240, number of turns in the primary is 1000, then voltage in the secondary is 12, number of turns in the sorry about this, we have to come back to this again. I have to clean this and say that here we needed to say number of turns in the secondary. Okay, sorry about that. So we continue and say, now when we put like this, we find the voltage in the secondary is 12 and number of turns in the secondary is X. So we look for X and we say 240X is equal to 12 times 1000, so that X becomes we divide and we get almost a half there, and then when we say 2 into 100 we get 50. So the number of turns in the secondary coil is 50. It agrees because this is a step-down transformer. So, we have to check the input current, which is here, because we have the output current is 3. We can only get it from the principle of conservation of power. So, we say power in the primary should be equal to power in the secondary. But power in the primary means voltage in the primary times current in the primary. That should be equal to voltage in the secondary times current in the secondary. So when we do that, we find that voltage in the primary is 240. Current in the primary is the one we are looking for. Voltage in the secondary is 12. Current in the secondary is 3. So current in the primary, therefore, becomes 12 times 3 divided by 240. So when we do that, what we realize is that this is now 3 out of 20, which gives us 0. Okay, 0.1 probably 5, okay, amps. So the pair that gives us the right answer is A. Number of tens 50, current 0.15. Next question. Right, before we go to the next question, we break for a while, and then when we come back, we continue with the other questions. Thank you, viewers, for being with us and still sticking to us and following us on this MTN Teleschool. Thank you. See you when we come back.
I told the bus driver that I work hard for my money, so it better gets to Chipata.
Yeah, that's right. That's what I told him.
Yeah.
Weather, drama nizingono, or nizambili.
Tituma. And he kept trying to tell us something, but I was like, Ukagamba, Tiloa.
Cause cash money yeve across Zambia.
Tituma. At bus and Kuchpat. The end of South Africa. Hello, what?
Run, K-Star, run! You got the bus.
Sending money doesn't have to be this dramatic. Open an MTN mobile money account today and send money to friends and loved ones across Zambia instantly. Dial *303# to send money with MTN, Zambia's #1 network. With MTN mobile money, Tituma.
MTN, everywhere you go.
Do you expect more from your internet service? Maybe it's time to switch to MTN's 4G internet. Introducing the next level in high-performance mobile network technology, taking your home or office internet experience to a whole new level while keeping it simple. Get to work by the click of a button or manage your team from miles away. Browse faster, download multiple files and stream videos quicker with no limits. Get it all done with MTN's 4G internet. So don't let your internet slow you down. Stay online in real time all the time. Get your MTN 4G SIM today and find your nearest 4G zone to enjoy maximum performance of your 4G enabled device. MTN, everywhere you go.
Welcome back, viewers, to the MTN Teleschool. Thank you very much, Mlenga, for your comment. Mlenga Kalilo. Thank you so much. We continue with question 35. The diagram below represents a cathode ray tube. Which part ABCD deflects the electrons? When we check on all these, we see that B is a filament which releases the electrons, and the only part which seems to be agreeing with the answer is C. D is a screen, so we can't rely on it. So we choose C. We move on. It's a fairly straightforward question. Question 36. The diagram below shows a circuit for a buzzer. So we can see that circuit there, and then what we notice is that, let me just draw something very quickly out of this circuit. What we see is that there's a switch here, and okay, let me just do it properly here. Okay, so we see a switch here. We see another switch here, and then we see it continuing to the buzzer. Okay, let's not be interested in the other part. What is very interesting here is what is happening here. What we see is that basically the circuit must be switched on. How? Either of these switches should be able to switch on this circuit. So either this one or this one. So the gate we are actually looking for is an OR gate. That's the switch we are looking for. So either this or that one should be able to switch on this. Either this or this one. So we are looking for an OR gate. And an OR gate is represented by D. Because B is a NOR gate. A is an AND gate. C is a NAND gate. So those do not qualify. 37. People working with radioactive materials use photographium badge covered in paper. The badge is used to monitor the level of their exposure to radiation. Which radiation is detected? We must understand very quickly here that we are discussing alpha particles. We are discussing beta particles. We are discussing gamma rays. These are the three basically we discuss all the time when we're discussing radioactivity. Now, out of these, we notice that these only travel few millimeters in air, and they are easily stopped by pieces of paper, thin pieces of paper. The beta particles do penetrate through pieces of paper, but they are stopped by thin layers of aluminum foils. Gamma rays can neither be stopped by thin layers of aluminum foils nor pieces of paper. So therefore they cannot be used. So this cannot be detected in this manner. This will not be detected in that manner because they will easily be stopped by any thin piece of paper. So the right one is beta particles only. Question 38. The activity of a radioactive source was observed and measured. The diagram below shows the graph plotted from the results obtained. Let's look at what was plotted here again. This is roughly the graph of a radioactive decay process. Now, it starts at 200 roughly, and then the curve comes all the way up to some point which is 12. Okay, so the way we can work out here it's time in minutes, and here counts per minute. Let me just write properly here. Counts per minute. So our main issue is the question which says, what is the half-life of the source? What is the half-life of the source? Half-life by definition is the time that it takes for a radioactive sample to have either its mass reduced by half or the count rate reduced to half its original value. So we are talking about the original starting point, either in mass or the count rate. In this case, we are given the count rate. So we can go to the initial count rate and divide it by 2. Then we are going to come to roughly where it shows 100. And then we go with that and meet the graph here. And come down here and check the time that it is showing. What we see there is approximately 3 minutes. And then we again divide 100 into half. So we get 50 and we follow it like this. And we come and check the time it's showing here. We find 6. The difference between 3 and 6 is actually 3. So you have T1 and you have T2. So it shows that averagely T1 plus T2 divided by 2 gives us the half-life, which means 3 plus 3 divided by 2, which is 6 divided by 2, giving us 3 minutes. That becomes approximately our half-life of this sample. Question 39. Alpha, beta, and gamma radiations, 1, are absorbed to different extents in solids. 2, behave differently in electric fields. 3, behave differently in magnetic fields. The diagrams 39A, 39B, and 39C illustrate these behaviors. As you can see those diagrams, viewers, when we look at those diagrams, what we see is that the question says, for example, which 3 labels on these diagrams refer to the same kind of radiation? That's what they are asking. Which 3 labels on these diagrams refer to the same kind of radiation? In this case, we can trace one by one if we wish. We just trace one by one. In fact, the first thing is to identify these ones by the behavior, as I explained earlier on, to say that alpha particles do not go far and they are easily absorbed by thin pieces of paper. Beta particles pass through easily the pieces of paper, but they get to be absorbed by thin pieces of aluminium. While gamma rays do not get to be absorbed by any of these, and they simply pass through. So based on that one, let's try and check now. We notice that A says LQX. Let's follow that. L is stopped, which is alpha. Q here passes straight and deviated. The behavior of gamma rays is that it is not affected by magnetic fields. It does not get stopped by any material. So it contradicts. When we check on B, we start with L, which we suspect alpha particles. P, when we notice P on B, diagram B, we notice that alpha particles are getting attracted to the positive, which is wrong because alpha particles are positively charged, so they cannot be attracted towards the positive. So that collapses. C, we go to M, we see that that could be suspected to be beta particles. Then when we go to M, we are saying M is suspected to be beta particles. We go to P here, and we notice in B that these beta particles, which are negatively charged, are being attracted to the positive. It agrees. And then we go to Z. When we go to Z, we see that they are being affected by magnetic fields correctly. So this depicts the correct response to this particular question. And so if we checked the other one, we notice N is gamma. So we go to Q, which is gamma, but X is contradicting. So we are left with only one choice, which is C, as the right answer. Well, viewers, we can move on to the last but not the least in this session, which is question 40. the daughter nucleon number is 14 and proton number is 7. Which of the following shows that the parent radioisotope emitted a beta particle? That is the question. Now, when we want to answer this question, we must understand something to say the word nucleon refers to the number of protons plus neutrons in the nucleus of an atom. Proton number refers to the number of protons in the nucleus of an atom. But again, we must understand the fact that the question says which of the following shows that the parent radioisotope emitted a beta particle. We must understand what is a beta particle. It's a fast moving electron which has been ejected from the nucleus of an atom. Now, how does this happen? Inside the nucleus of an atom, one neutron decays into a proton and an electron. One neutron decays inside the nucleus to form a proton and an electron. Now, this electron is what is ejected in form of a beta particle because it cannot sit inside the nucleus. When this is ejected out of there, what it means basically is that the number of neutrons has reduced by 1, while the number of protons have increased by 1. This means that the nucleon number, meaning the total number of protons and neutrons, remains the same, which is 14. Okay? And then the proton number increases by 1, which means 7. Here they are asking about where we are coming from. So it means that where we are coming from, this X, the parent radioisotope, was at position number 6 and nucleon number 14. So that with the emission of a beta particle, then it went into Y, which had 14 and 7 as proton numbers. So the answer is nucleon number should be 14, atomic number should be 6. Atomic number, mind you, is the same as proton number. Well, viewers, we've come to the end of this session. I'm happy, I'm pleased to have interacted with you this period, and I hope that we will be together in the next session as well, and I hope that your contributions will be coming as we continue to discuss this matter concerning physics. Well, Mulenga, thank you so much again for being with us. We hope that you will invite your friends also to be with us in the next session. It's been a pleasure. And my name's again James Kabuye, specialized in physics, and we've been together going through these questions, and I humbly request you to be with us in the next session as well. Please be happy, yellow, and thank you. Good afternoon.
Tiende pamoja ni mtima umo. 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 Tiende pamoja ni mtima umo.